Okay, well then this gets down to a comparison of the bottom up versus the top down. By bottom up, I mean the particles build up the reality from the bottom up. Things get more complex as you go up. The top down is you have the probability of how the reality works, okay? And then that then generates the change in the data stream, which informs our reality of what's going on. Okay, well there's 4 main issues here that I'd just like to mention. One is that the bottom up starts with elementary particles. Okay, these are elementary particles that they're called fundamental particles. There's a problem, number 1, is with elementary particles. An elementary particle isn't composed of anything. Okay, if it's truly fundamental, it doesn't have any piece parts. So we used to think that about the atom. Then the atom had a nucleus and it had electrons. And we used to think that about the electron, and now the electron has quarks. And then the nucleus has protons and neutrons. And now the protons and neutrons get broken apart, and everything that used to be elementary becomes complex, and there's something else that's elementary. So now we have this set of elementary particles that we call elementary, and they're fundamental. But the problem is, if it's elementary and it has no piece parts, how do you get it? Where does it come from? You see, it's not made from anything. It's got no piece parts. So there's no way to make one. No way to make one. How do you get it? You know, well, they just are. They are because they are is the answer. It exists because they exist. And if you want to cheat this a little bit, you'd say, well, they happened in the Big Bang somehow. They just got made, but how do you make something again with no piece parts? You know, where did they come from? And besides that, the Big Bang, all right, let's even give you that. Where did the Big Bang come from? So it's the same problem. Popped out of nowhere, just is. So your elementary particles that this whole reality is built on just popped out of nowhere. That doesn't give you a real warm feeling, right, about the results that you're going to get from this calculation. So they're elementary, and they're fundamental. Okay, now that they're fundamental also has a problem, and that problem is that none of these particles have ever been observed or measured. None of them have ever been observed or measured. What has been observed or measured are the effects of these particles, right? So we see an effect, like the gravity was an effect. Things fall down, that's an effect, right? Now let's explain that effect. Well, maybe it's that masses attract. Maybe it's curvature space-time. Maybe it's electromagnetic. See, that's different. So the particle is just a hypothetical model of what somebody dreamed up to tell you how the effect works. So these are models. They're hypothetical particles. So one, they're elementary, which makes it difficult to where they come from. Secondly, they're fundamental, which means they're just theories. They're just hypothetical. Nobody's ever seen one. Nobody's ever measured one. We make them up to solve the problem of why do we get this effect? Like the masses attract. We make that up to solve where do we get this gravity effect, or the curved space-time. That just gets made up to say where do we get this gravity effect, you see? And there's often multiple ways that you can describe something, right? You get different viewpoints, different ways of describing all kinds of things. So we describe it with particles. And the fact is, back in the early 1900s, when quantum mechanics was just getting started, they had a big argument among physicists at that time. And the argument was, we have a perfectly good probabilistic model here that could explain all this. And that was Niels Bohr, Copenhagen, said that. And the other physicists said, well, but that's kind of weird, you know, probability. I mean, we're used to Newton and these little particles and everything's mass, and we understand that real good. We don't like that. It's too weird. We like particles. So at that point, back in the early 1900s, a decision was made to go with the particles because that feels better to us, because science has always been committed to materialism, and there you are with the particles. So a decision was made to go with the particles, and they have. And they've been down that rabbit hole, you know, ever since the early 1900s. So That's why they're having so many problems now trying to say, well, how does a double slit experiment work? You know, why do particles act like that? Well, it's because particle was a wrong way to model the problem. It's not a good model to explain the effects. You see, so it falls down. So we say these fundamental particles are hypothetical particles. And they're elementary, which means they pop out of nothing. So we see materialism now doesn't have exactly a real strong, logical foundation underneath of it. It's starting to look pretty ratty at the roots. The third problem is that consciousness exists. Of course, the materialists may deny that it exists, but I think most everybody knows that we are conscious and we make decisions, and we could make this decision or that decision, and events will change based on the decisions we make, and that seems pretty obvious to most of us. But in any case, they want to show how that could happen out of particles, but they can't. Not only they can't even come up with a good model of how that could possibly work. How do you put the Legos together to build this real complex Lego thing, and then it becomes conscious because of the Legos? See, that just doesn't fly very well. It's not rational. So they call that the hard problem. And if you Google consciousness studies, you'll find the hard problem. The hard problem is, how do you take a bunch of inanimate chunks of particles and end up with consciousness? No ideas. If they had an idea, they jump on it, but there's just no way to connect those two. So that's the third problem. Things like consciousness now disappear. The fourth problem is the complexity and the processing requirements to work a materialistic model. Everything, every action has to be computed from the ground up every time because it's different. So I raise my arm and I put it down. Whole bunch of molecules and atoms just went through a whole lot of motions that would take a supercomputer days to compute, and I do it again, and guess what? It didn't go in exactly the same place it did last time. It all has to be computed from the ground up again. So I keep doing this, and I keep driving that supercomputer crazy because it can't keep up, you see. So why would you go through all of that computation if you didn't have to? So it's inefficient. And we have a thing in science called Occam's razor, which says if processes really don't make any sense, if they're not efficient, if they're not pared down to the simplest way that you could solve the problem, they're probably wrong. And you apply Occam's razor to that, and it would toss determinism out in a second because it's so complicated to build a world out of particles. So those are four things that just don't add up. And that's the foundation under which all the rest of science is based, you see. That's the basic foundation. So these elementary fundamental particles aren't too solid logically, and it's a very good guess. I'll say another one of these things that is falsifiable. When they have the tools to tear these elementary fundamental particles apart, they will find more elementary fundamental particles. And the old ones then will be complex particles, and they'll have new fundamental particles that popped out of nowhere. So that's a prediction of mine, and the reason I say that is that the way the reality works is that if you have something and you don't know what's inside and you break it apart, the larger consciousness system takes a random draw from a probability distribution of what might be in there, and that's what you're going to see. And of course, it also has to be consistent with what we know, with everything else that we know. And that's what you're going to see. Now, eventually, you'll get down to the bottom of the resolution of the virtual reality, and then you're stuck. You're not going to break that apart. So we do end up with something that's fundamental. And we'd say, aha, well, we get to the end, there's something that pops out of nothing. No, it doesn't have to pop out of nothing. You're stuck with pops out of nothing if you're a materialist. If you are doing a probabilistic virtual reality, it's simply the initial conditions. How big is delta t? How big is delta x? What are the initial conditions that you put when you do this? What are the limits of your simulation? Well, that's the bottom. It doesn't have to pop out of nothing. It's an initial condition. It's simply explained. But where we're measuring now, even our tiniest little particle, even the little Higgs they just found, we're so excited about, that is a long, long way from hitting the limits of resolution. They have orders and orders and orders of magnitude to go before they get down to our resolution of this virtual reality, down to the Planck length and the Planck time. So what's the probability that what they've hit on now is fundamental? Very, very, very small probability. When they tear that apart, there's going to be something else. And then when they find they can tear that something else apart, there's going to be something else, because they've got like 20 orders of magnitude to go before they hit the bottom of the stack. So they're neither elementary nor fundamental. And it's a crazy way to run a reality. All right. So generation of our PMR. PMR for the newbies is physical matter reality. That's our universe we live in. Okay, the first 5 of these are just for background. The first 5 basically explain how the larger consciousness system started, and we get down to like the 6th bullet. New facts enter, physical reality by a random draw from a probability distribution of those possibilities that are consistent with all former PMR facts. Once new facts exist in the physical world, they join the set of former PMR facts, as long as their defining information is available in the physical reality. So that's it. So we don't have to build a whole lot of things up out of little things. All we have to do is create the probability distributions, run the problem, model the rule set once, get the probability distributions, and a lot of things that happen on this planet, like me just putting my arm up in the air and taking it down, you don't have to do new probability distribution for that. If it went up and was a millimeter this way instead of that way, you don't notice, nor do you care. You see, so we don't have to do that to the atoms and molecules and things. It just, you get a point where it's good enough. So anyway, that's really all there is to it. So with top-down logic, first we start with the assumption of fundamental consciousness, and we allow the process of evolution to step by step logically derive everything else. It's just that simple. Okay, now this one, I don't want that to scare you. This really won't hurt. I want to explain to you what it means to say take a random draw from the probability distribution, because you hear me say that over and over again, and most of you probably think that there's a bunch of possibilities out there and you randomly just reach up and grab one. That's not what's going on at all. In that case, every possibility would have the same likelihood of being drawn. It doesn't. That's why we have the probability distribution. We have 26 possibilities here. 26 possibilities. So from A to Z. A is a possibility, B is a possibility, C, okay, 26 different possibilities that could happen. Now, this is a probability distribution. This line goes up here and here and here and so on and back down, and that's the probability distribution. And many of you think of probability distributions as either being uniform, which all of the possibilities have the same probability, or kind of Gaussian, which is the bell curve. It starts low, goes up, and comes down. Well, those are the nice, neat, easy things to work with that we do, but real probability distributions that describe the real world can be any kind of ugly thing. It doesn't have to be something nice and pretty or symmetric. So this one I just made up, and that means that there's one A here, that's what the 1 is. There's 2B here, that's what the 2, and so on. There's 6 H's here, and that's the 6. So each one of these letters has a probability that's represented by the number of those letters that are in here. Okay? So what a probability distribution is, it gives you the relative probability between the different possibilities. So this 25, these K's, is 25 times more likely, more probable than this D or E, which is 1. Okay? And the L, look at the L. It's 7 times more probable than, say, the G, because here's the L and it's at 21, and here's the G at 3. So it's 7 times more probable than the G. So you see, it's just simple arithmetic there. So this is a probability distribution. Now here's what it means to take a random draw from the probability distribution. You take all these letters Now all these letters turns out to be, there's 165 letters under this distribution. Okay, so I mean that's 1 plus 2 plus 2 plus 1 plus 1 plus 2 plus 3 plus 6, and just keep doing that all the way there to count all the letters, and you get 165 letters. I'm sure somebody's going to count them and see if I did it right, but anyway, that's what it is. So here's what you do, is you take all 165 letters, you put them in a box, you shake them up, turn the box upside down, shake it again, reach in, random draw, pull one out, and that's the possibility that happens. That's the one you get. Well, you see they're all not likely. The same, I mean, they're all not as likely as each other. You know, the Z and the D and the E, very likely out of 165, you're going to pull one of those out. You could, but it's just unlikely. You're most likely to pull out a K, because there's 25 of those in there, you see? That's what I mean. So you take a random draw on the distribution, means that you pull things out according to the probability. Now, of course, when we do math, for those of you out here doing math, he's thinking, what is it? Why does that stack of K's up there? What do you mean you put them in a box? You know, this doesn't sound too scientific, right? Putting things in a box. But it makes it easier for me to explain it to you. What's really going on in there is that you take all the probabilities. Here's one way to look at it. There's several ways mathematically. You take all the probabilities, you find the smallest one. Okay, you multiply the smallest one by a number that's the inverse of that probability. So when you multiply something times inverse, you get 1. So if that smallest number is 1 over 1,000, then you multiply it by 1,000, you get 1. Then you multiply every other probability in the set by 1,000. Now you've normalized them all, and you end up with a distribution like this. And now you can just add up all the numbers of all the probabilities, and that's what you divide by, instead of the 165. So see, that's kind of mathy. You know, putting them in a box is easy to understand. And then if you want to go to the next level, each one of these little towers here of letters represents a certain amount of area under the curve, and you use integral calculus to measure the area under the curve of the various things, and then the total area under the whole curve is the total, is what you divide by. So there's just, you know, there are actual ways that mathematicians do this without putting little slips of paper into boxes and shaking them upside down and pulling out things. But that's a good metaphor that you can use for what it means to randomly pull something out of a distribution. So that's the point. And I can show you some of the probabilities here. So the K's are 25 divided by 165. That's their probability. You see? So it's always going to be less than 1, because you're taking the area under the curve in a little piece, divided by the area under the whole curve. So it's always, probabilities always have to be less than 1. So what's the probability that you'd get any one of these letters from A to Z? 1, because you'd take all the area under the curve and divide it by all the area under the curve, and if you reach in the box, you will pull out a letter. So the probability of getting one of the letters is 1. You see, the probability of getting any particular letter depends on the relative probabilities between the letters. All right, so now we're up to the end of a top level comparison. We're going to kind of compare the particles and materialism to the top-down logic of consciousness and virtual reality. You'll notice one thing is that both of them have the word somehow in it. I tried to emphasize that. They both have that because they both have to start on an assumption. So we don't penalize the deterministic way or the material way because they start with an assumption. We start with an assumption because there's limits on knowledge and we can't know everything. So an assumption is not a failure of process, it's just a fact of life. We start with an assumption, so they both do. But after that, and the assumptions they make are very different, okay? In the bottom up, we start with the assumption that the micro world of 61 theoretical particles based on 19 arbitrary constants, those arbitrary constants were just made up so that the description of the particle would fit the measurement that was made. So that's the way it is. You make a particle, but a particle doesn't work so well, then, you know, we used to call that fudge factor. You know, you'd multiply what you got by a number you needed to get the right answer. You know, that was a fudge factor, but it kind of works like that. You get these particles, and in order to make them fit what you want, you multiply them by constants to shift them around and make them fit the theory. instead of making the theory fit the, they do it the other way around. So the 61 theoretical particles, 19 arbitrary constants, I just pulled that out of Wikipedia. That they somehow exist without a source, without a cause, without explanation, and then we construct the physical world from these hypothetical particle models, and somehow a mysterious process we don't understand creates consciousness. Thus, we come up with a bottoms-up worldview that can explain a limited set of facts about the physical world. Now, the top-down logic is we start with the assumption of fundamental consciousness that somehow, emerges from random process into complexity. But now that's not pops out of nowhere. That's a process given credibility with mathematics. We can show how this can happen, how that might work. But we start with the assumption. Then we allow the process of evolution to logically explain the physical, metaphysical, philosophical, and theological facts of the larger reality, including explaining much PMR experimental data that cannot be explained by the bottom-up approach. Thus, we come up with a top-down approach that explains the larger reality, our universe, and its mechanics, its purpose, its function. Additionally, it explains our individual and collective connection and responsibility to that larger reality and to each other. So the top-down approach generates a logical and scientific foundation under the wisdom collected and refined over thousands of years of human subjective experience, as well as contains all of contemporary physical science as a subset. So that's kind of the comparison between these two ways of approaching the nature of reality.